Alright, welcome to another AP Physics 1 video, of course not sponsored by AP College Board, and we'll be looking at another FRQ here. The first thing that we want to do when we look at any FRQ is determine what the problem could be testing us on. Well, we're given the mass, we're given a certain force that a student exerts on let's say a disk, over a time interval. Well, that's making me think of impulse. And if I am given the mass, well, that's making me think of the impulse momentum theorem, where the change in momentum is the impulse, which is the exerted force multiplied by delta t. So maybe this problem is a momentum problem then. And my suspicions are confirmed when I look at part C, when I see a disk literally flying towards a block. This is a collision problem. This will probably be a momentum problem. Okay, so now I have to decide what I want to do with this problem. And what I mean by that, which part I want to start with this problem. Should I start with part A or part B or part C? Well, for part A, it looks like this is a standard mathematical question that I could do. And by the looks of it, part B seems to be a question where I kind of have to rely on my answers for part A to do it. And part C seems to be something that seems related at first, but now we realize that actually it's not that related because we're given the speed that the disk is traveling at v1. That's not the speeds that we're given over here, so that'll be unrelated. And we're actually given nothing else that's actually connected with part A and B. There's no more student in the problem anymore, and the only thing that's constant in these problems is a disk. So in that case, we could actually start with part C first before we go with part A and B. Now let's just say that for part A and B, I forgot the impulse momentum theorem. So I had to start with part C first, and that's a very important skill that all of you should have because you have to admit sometimes where you realize you can't actually do a part and you have to jump to the next part or a part that makes sense. And for this part, if you forgot how to use the impulse momentum theorem, then you probably can't do part AI or AII. So that also means you probably can't do part B. So what that means is probably you have to go with part C then. And that's okay because you could still do part C and do pretty well on the exam because you could fail an entire FRQ and still get a 5 on the exam. In fact, you could do that for 2 FRQs now and you'd still be fine. It kind of depends on what FRQs you bomb, but as long as if you're able to do the experimental design and the quantitative translations, you could miss out on the other 2 FRQs and you'd be fine. And now this problem is actually a quantitative translation. It's not a translation between representation, so you probably do want to be able to do all parts of this problem, but it's fine if you're able to do half of it, as long as if you're able to do the other FRQs. Once again, no pressure. Okay, for part C, we have to determine an expression for the velocity of a center of mass if the mass of a disk is much greater than the mass of a block. Well, we could think of a very, very massive disk traveling at a constant speed vi, hurtling towards a small, small block. Well, the block isn't going to do anything to the disk, so the velocity of a system should in theory still be the same. So it should be still v1. Alright, there's no difference for it to be not v1. Okay, so with that, we still have to explain how we arrived at our prediction. So we should probably write, since the surface does not have any friction as given by the problem, the initial velocity that the disk will be traveling towards the block will basically be unchanged by the minute block's mass. This is a result of Newton's second law, where while, according to Newton's third law, both masses actually experience the same force, because a disk is much more massive and has much more inertia than the block, its experience acceleration would be much less, and thus its velocity or its speed will change much less. So that's why its speed will be v1. Now, on the other hand, if a mass of a disk is much less of a mass of a block, well, that probably means that all the speed will be killed off, or even if it's not killed off, because of how massive a block is, the speed of a disk will be basically insignificant, no matter how fast it's traveling at, basically. So even if a disk was traveling at a very fast speed, because of how massive a block is, it won't matter. So the speed is zero. So what we could say is, because of how massive the block could be, any fast speed that the disk may possess would be insignificant to the disk block system. Hence, the disk block system's center of masses velocity will be approximately zero. All right, and that'd be our reasoning as to why that's the case. Okay, so now we have part C, I, and II out of the case. We see that in part III, we actually have to do some math. And I'm realizing, well, I have to derive an equation for velocity of a center of mass. I have to express my answer in terms of these quantities. This seems like a momentum problem to me. Now, before I actually do this problem, I have to read this question a bit carefully because I have to determine if this collision is an elastic collision or a inelastic collision. And we're given that the disk and the block collide head-on and stick together. So it is an inelastic collision. So that's great news because now what we can say is that the final velocity of a system will be the velocity of a center of mass. Why do we know? Well, because they're stuck together, they have to be traveling at the same speeds, or else they won't be stuck together. So, our equation, our work would be this. Our P initial is equal to P final. Always write your first principles. So then, our P initial is solely the mass of a disk traveling, multiplied by the speed it was traveling at, which is equal to the center mass, or the final velocity, multiplied by the mass of a disk plus the mass of a block. All right, so now that we have that, all we really need to do is isolate for the velocity of the center of mass, and we get that the velocity of the disk initially traveling multiplied by its mass divided by its mass plus the mass of a block is the expression we want for the velocity of a center of mass. And it turns out that if you forgot everything about momentum, which is very tragic and you should review, you can actually still do this problem. Why? On the AP reference sheet, you're actually given the equation for the velocity of the center of mass. And that equation is actually sum of the mass multiplied by the velocity of an object divided by the sum of all of the masses in the system. So you can actually use this equation and apply that to this problem here to determine the exact same expression that we have just derived. So you can technically do this problem without any of the equations here that I've written out, and you'd still get full marks because you've written something out of the equation sheet. Okay, now for part IV, we have to consider what we had for a result in I3 and apply it to part I. Okay, well, that's no biggie. All we really need to do is analyze what is part I and its relationship with part III. Well, if the mass of a disk is much greater than the mass of a block, well, if we look at our denominator, that means that the mass of a block will probably become zero. So, what we should write is this. If the mass of the disk is much greater than the mass of a block, then the denominator simplifies to MD because of the insignificance of the term MB. This means that the fraction will equate V1 as MD cancel out on the numerator and the denominator. All right. So our answer, in fact, makes sense, and in theory, it should be because that's normally how the AP exam works. So don't forget to do a quick check mark all the way over here. And a quick tip is that for questions where we ask you to verify if what you derive, not what the problem told you, if what you derive makes sense, you should always answer with yes if you have time, and you should always figure out how to make your answer make sense. Why? Because these problems are normally designed to make you check your work. So if you answer no, that means you've actually done something wrong. Now, this little trick doesn't actually apply to problems where they give you an equation and ask you if this equation makes sense. The answer could be no in that case, and you still have to justify it with why it doesn't make sense reasonably. But for problems like these, you would normally answer yes because they're asking you to check your work. Now, of course, if you're running out of time, you should probably answer no if your answer doesn't actually make sense or isn't consistent just for part mark's sake. But do realize that you probably lose all your marks for what you did before because it is wrong. So always make sure that your answer is yes when you ever justify your reasoning. And if you do select yes, don't worry about that problem much anymore because you probably did it right. Okay, so that is part C now. Let's actually deal with part A and B. So, unfortunately, here we do have to use the impulse momentum theorem, but hey, now you know that exists. What that is the impulse J is equal to the change in momentum, and that's given on your equation sheet, which is equal to P final minus P initial. And since we know that the disk begins at rest, we can reasonably equate this just equal to PF. All right? So now with this expression, what we could do is say that, well, the impulse is the force exerted over the time interval from 0 to TF. That's just FH multiplied by TF minus 0. That's just TF. This is equal to, well, PF is equal to M multiplied by VF. That's the mass of the disk because the student is exerting a force on the disk multiplied by the velocity of the disk, VD. So if we isolate for VD, we should get that the force exerted on the disk over the time interval TF minus 0 divided by the mass of the disk is the velocity of a disk after the pole loses contact with the disk. Okay, so that's our answer to I. Let's look at II now. We're given that there is negligible friction between the student's shoes and the surface. So that means that Newton's third law actually applies here. So what we can say is the magnitude of force exerted on the student is literally FH due to Newton's third law. All right? You don't need to explain why it's due to Newton's third law, but it'd still be nice if you explain why, because they're part of the same system, and there was a collision and there were no external forces involved. So because of this, actually all we really need to do is copy out our derivation before. So we write that the impulse is equal to PF, and we could write that the force exerted on the student because of a pole colliding with a disk over the time interval TF minus 0 is equal to the mass of a student multiplied by the velocity of a student. And what we get is that the velocity of a student is equal to FH multiplied by TF divided by MS. All right. Now, we can't stop there because it's asking us to derive an equation for the ratio VD divided by VS. So if you just wrote this, we wouldn't get full marks for the question. So we have to continue then that VD divided by VS, we notice that FH and TF both cancel out. So what we get is that this is equal to 1 over MD divided by 1 over MS. And if we do a flippy dippy, hopefully with algebra, you realize that that's just equal to MS divided by MD. So that is our final expression for the ratio VD over VS, and we are done for all of part A now. Cool. So now we have to deal with part B. We have to assume that the student's mass is much greater than the disk, okay? And we have to draw out what happens after the pole or the stick leaves the disk at time t equals to tf. So over here, the collision stops. So what that means is because there are no external forces, there's no friction or whatever, there's no ramp, there's no gravity, there's a net force acting off a system after TF, their speeds will be constant in this little section here. So that means that there will be probably an increase in speed here, and there's going to be a constant speed over here. Now, will this increase in speed be linear or will it be quadratic? Well, it will be linear. How do we know that? We are given that it is a constant horizontal force with a magnitude Fh that's being exerted. Well, a constant force means a constant acceleration. That means a constant increase in velocity. Well, you should remember that acceleration is simply the change in velocity over change in time. So the slope will actually be linear in this case. There's no need for a quadratic slope. Okay, so now that we have this, we have to determine if ms or md will be on top. Well, first of all, we know that ms is greater than md. Cool. If ms is greater than md, that means that this fraction will be greater than 1. If it's greater than 1, that suggests that vd will be greater than vs. Aha, so that means that the disk will be traveling at a greater speed than the student. And that makes sense if you think about this qualitatively. Based on Newton's first law, if a student is much greater than the mass of a disk, that means that the student will probably change its velocity much less than the disk. All right? So that means that we'd have a linear slope that looks all the way like this. And probably it'll be something like this. And we simply connect the lines. Let me redraw that line. We simply connect the lines all the way up here. And the velocity of a student here would probably, this is just purely based on speculation, you don't actually need to calculate any expressions, it would be something like this. And then we know that their speeds will be constant in the end, so we could just draw a straight line. And we could just draw a straight line in the end. All right, so once we have that, our final solution actually becomes really simple. All we really need to do is label the graph of S and D. Well, we know that the velocity of the disk will be greater, so we write D here because it's higher, it has a higher speed, and we'll write student S here because, well, it has a lower speed than the disk. And after that, we're actually done because we don't have to label anything else because we're not asked to label the relative sizes because we don't know their actual ratios. So that's it. We are now officially done for for the third question in the AP Physics 1 2021 Momentum FRQ. And that's it for the quantitative translation part of this FRQ for the exam. All right, that does it. I'll hope to catch you on the next one. If there's any feedback you'd like to give me because of how boring this may be or how uninstructive this may be, feel free to tell me in the comments below or send me a DM. And I hope to catch you on the next one. See you soon.